Today, we will discuss one of the most astounding results in Ramanujan's work. 1 plus 2 plus 3 plus 4 and so on is equal to -1 by 12. Common sense says it can't be true. How can the sum of positive integers be equal to a negative fraction? Today, we will find out how the famous YouTube channel Numberphile proved it and why their proof is mathematically incorrect. And to truly understand and appreciate the result, we will prove the result using Ramanujan Summation and Riemann Zeta function. In the end, we will explore whether there can be possible applications of this astounding result. In 2014, a famous educational YouTube channel, Numberphile, published a video in which two physics professors from University of Nottingham, using elementary arithmetic, proved 1 plus 2 plus 3 plus 4 and so on is equal to -1 by 12. That is, the sum of all natural numbers is -1 by 12. The link of that video is in the description below. Now, all of us have studied the basic formula of partial sum of natural numbers. Sn is equal to 1 plus 2 plus 3 plus so on plus n is equal to n into n plus 1 whole by 2, which clearly shows that as n approaches infinity, this partial sum diverges, which simply means the sum of all natural numbers should diverge to plus infinity. So, did Ramanujan, or for that matter the university physics professor, not study this basic formula? The result is so weird that even Ramanujan in his letter to Hardy wrote, "Dear Sir, I was expecting a reply from you, similar to the one which mathematics professor at London wrote, asking me to study carefully Bromwich's infinite series and not fall into the pitfalls of divergent series. I told him that the sum of an infinite number of terms of the series 1 plus 2 plus 3 plus 4 and so on is equal to -1 by 12, under my theory. If I tell you this, at once you will point out to me the lunatic asylum as my goal." Now, before we actually judge his sensibilities and pass our judgment, we will first look at Numberphile's method of proof. They started with a series 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on, and let its sum be some constant S1. Now, write the same series again, but after displacing one term to the right. If we add the two series, we get the result 2S1 is equal to 1, which is S1 is equal to 1 by 2. Then they considered another series 1 minus 2 plus 3 minus 4 plus and so on, and let its sum be some other constant, S2. Write the same series again, but after displacing one term to the right. If we add the two series together, we get 2S2 is equal to 1 minus 1 plus 1 minus 1 plus 1, which is S1. So, 2S2 is equal to 1 by 2, that is, S2 is equal to 1 by 4. And now they considered the series in contention, 1 plus 2 plus 3 plus 4, and so on, and let its sum be S. Now we will find S minus S2, which is 1 plus 2 plus 3 plus 4, and so on, minus 1 minus 2 plus 3 minus 4, and so on. We get S minus S2 is equal to 1 minus 1 gets cancelled. 2 plus 2 is equal to 4. 3 minus 3 gets cancelled. 4 plus 4 is equal to 8. So we get S minus S2 is equal to 4 plus 8 plus 12, and so on. Now, we can take 4 common on the right hand side. We can write S minus S2 is equal to 4 taken common, and in brackets 1 plus 2 plus 3 plus 4, and so on. And 1 plus 2 plus 3 plus 4 is nothing but S. So now we have S minus S2 is equal to 4S, which is minus 3S is equal to S2. We already know that S2 is equal to 1 by 4. So we get minus 3S is equal to 1 by 4. That is, S is equal to minus 1 by 12. Here goes the astounding result. 1 plus 2 plus 3 plus 4 and so on is equal to minus 1 by 12. This video garnered tremendous response, and by now it has over 7.2 million views. It was even covered by New York Times in an article titled, "In the End, it all adds up to minus 1 by 12. This video also invited the wrath and fury of mathematicians and mathematics enthusiasts. They termed the methods and results as preposterous and misleading. A large number of mathematicians took to social media and expressed their anger and disappointment at their cheeky attempt to engage wider audience at the expense of academic rigor and authenticity. Of all the noteworthy attempts to refute the methods used in the proof, I will choose a video posted in 2018 by another famous YouTube channel, Mathologer. The video was titled Numberphile versus Maths, 1 plus 2 plus 3 plus 4 and so on equals minus 1 by 12, debunked. The link for this video is also in the description below. In this video, Mathologer explains that all three results in Numberphile's video are false. Before we proceed, let us take a quick recap of convergent and divergent series. An infinite series is a convergent if the sequence of the partial sum approaches a unique finite limit, else it is divergent.
Now say for example, this series 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 16 and it goes up to infinite. Now we'll consider their partial sum. Suppose S1 is 1 by 2, S2, so which is 1 by 2 plus 1 by 4, and that is 3 by 4, S3, sum of first three terms, 1 by 2 plus 1 by 4 plus 1 by 8, and that is 7 by 8, S4, 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 16, so it is 15 by 16. If we'll keep adding more and more terms, this sequence approaches 1. So we can say this series converges and its sum is 1. And of course we know that the sum of an infinite GP is A upon 1 minus R. So here in this case, value of A is 1 by 2 and R also is 1 by 2, which again is 1. So this series, it is a convergent series.
Now, we will consider the partial sums in relation to the three numberphile series. The first series was 1, minus 1, plus 1, minus 1, and so on. The sequence of partial sums is 1, 0, 1, 0, and so on, which alternates between 0 and 1, and it means limit doesn't exist, which simply means this series diverges and doesn't have a sum. If we consider 1, minus 2, plus 3, minus 4, and so on, then the sequence of partial sums is 1, minus 1, 2, minus 2, 3, minus 3, which also alternates between plus infinity and minus infinity, and thus, again, does not have a sum. And for the series S is equal to 1 plus 2 plus 3 plus 4 and so on, the partial sums are 1, 3, 6, 10 and so on, which diverges to plus infinity, and that is the sum of the third series. So, basically, all the three series are divergent. The mathematical operations of adding the series or shifting to the right is valid in case of convergent series, but they are completely wrong in the case of a divergent series. So, mathematically speaking, all the three results in Numberphile's video are wrong. Now, what does that lead to? Are Ramanujan and the Numberphile guys insane? Ramanujan in his letter wrote, "I dilate on this simply to convince you that you will not be able to follow my methods of proof if I indicate the lines on which I proceed in a single letter." So, Ramanujan knew what he was working on, and for that matter, Numberphile physicists also knew very well that in standard summation, the result 1 plus 2 plus 3 plus 4 and so on is equal to -1 by 12 is incorrect. Ramanujan at that time was working on Riemann Zeta function regularization, and his summation assigns the series a value of -1 by 12. Numberphile got it wrong and invited wrath when they didn't clarify in the video that in 1 plus 2 plus 3 plus 4 and so on is equal to -1 by 12, it is not a regular sum, but a supersum, or in this case, Ramanujan's sum. In his blog post, Dr. Tony Padilla mentions that our video has engaged huge numbers of people with and without mathematical backgrounds, and got them debating divergent sums in internet forums and in the office. That cannot be a bad thing, and I'm sure the simplicity of the presentation contributed enormously to that. Whatever Dr. Padilla says is right in its own way, but I would also say that the end doesn't justify the means, and Numberphile guys advertently or inadvertently chose to mislead by not putting a disclaimer that their method and result doesn't hold in regular summation mathematics. Now, we know that all the three series diverge in regular summation. So, how do we make sense of these series? The first series, 1 minus 1 plus 1 minus 1, is called as Grandi's series, which is not summable in the usual sense, but if we take its Cesaro's summation, which is the arithmetic means of their partial sums, then its sum is 1 by 2. The second series, 1 minus 2 plus 3 minus 4 and so on, is neither regular summable nor Cesaro summable, but it sums to 1 by 4 using more powerful Abel summation. The third series, 1 plus 2 plus 3 plus 4, is not summable even with Abel's summation, and the series diverges to infinity. However, the Ramanujan sum of this series converges to -1 by 12 through several methods, including zeta functions regularization. Although the result -1 by 12 seems, at first, not to have any real significance, surprisingly, it yields a number of mathematically interesting consequences and has practical applications in physics.
So, now we will start with the Ramanujan summation. Wikipedia defines Ramanujan summation as a technique for assigning a value to divergent infinite series. It has properties which make it mathematically useful in the study of divergent infinite series, for which conventional summation is undefined. The idea of Ramanujan summation is based on Euler-Maclaurin summation formula. At around 1735, Euler and Maclaurin independently arrived at the formula which deals with the difference of integrals and a closely related sum. If m and n are natural numbers and f of x is a complex or real-valued continuous function for real numbers, x is in the interval m to n, then the integral m to n fx dx can be approximated as sum s is equal to f of m plus 1 plus f of m plus 2 till f of n.
So all of us know this rectangle method, right? So in which this integration can be approximated as sum of rectangles.
for a positive integer p and a function f of x that is p times continuously differentiable in the interval m to n, formula says
S minus is, the summation k varies from 1 to p bk upon factorial k f k minus 1 n minus f k minus 1 m plus rp, where this bk is kth Bernoulli number and rp is an error term which depends on n, m, p and f, and this rp is usually small for suitable values of p. Now we know that odd Bernoulli number, they are 0 except for b1. We know that b1 is 1 by 2. So this formula is generally written as summation fi, where I varies from m plus 1 to n, and this is integral of m to n fx dx plus fn minus fm divided by 2 and plus summation k varies from 1 to floor function of p by 2 and then b2k upon factorial 2k into f 2k minus 1n minus f 2k minus 1m plus rp. Now here this f 2k minus 1n is 2k minus 1th derivative of this function. Now what Ramanujan did was, he wrote this formula for the case when p goes to infinite. So Ramanujan wrote it as summation k varies from 1 to x fk, and this is c plus this integral from 0 to x ft dt and then plus 1 by 2 fx plus summation k varies from 1 to infinite b2k upon factorial 2k and f 2k minus 1 into x, where the c is a constant specific to the series and its analytic continuation. Now what Ramanujan proposed was to use this constant c0 as the sum of divergent series. So for a function f, this classical Ramanujan summation of series, which is summation k varies from 1 to infinite fk, is equal to this constant c0, and which is minus 1 by 2 f0 and then minus this summation k varies from 1 to infinite b2k upon factorial 2k f2k minus 1 at 0, and we know that b2 is 1 by 6. Now if in Ramanujan summation put fx as x, we know that f0 will be 0, f dash x will be 1 and f double dash x and all other derivatives, they'll all be 0. So in that case we can write this sum as summation k varies from 1 to infinite k, and this is minus 1 by 2 into 0 minus and then b2 upon factorial 2 f dash 0 and all other terms, they'll be simply 0. So then we can write the series as 1 plus 2 plus 3 plus 4 to infinite as minus 1 by 2. Now b2 is 1 by 6 and f dash 0 is simply 1. So it is minus 1 by 12. So this way Ramanujan has calculated sum of known divergent series, and it is important to note that it is not regular sum but Ramanujan sum. Whenever we write the series, we write it as R, which denotes it's not a regular sum but Ramanujan's sum.
in his personal notebook when Ramanujan wrote minus 3c is equal to 1 minus 2 plus 3 minus 4 and so on is equal to 1 by 1 plus 1 whole square is equal to 1 by 4. He, unlike Numberphile, didn't manipulate infinite series as if they were finite sums, but he used zeta function regularization, which is evident from his letter to Hardy. The result, 1 plus 2 plus 3 plus 4 and so on, is equal to minus 1 by 12, also flows from the work of another great mathematician of recent times, Bernard Riemann, and his equally famous work, Riemann Zeta function. Let me give you some context for Riemann Zeta function.
Now in his famous Basel problem, Euler famously proved that the sum of 1 upon 1 square plus 1 upon 2 square plus 1 upon 3 square up to infinite is equal to pi square upon 6.
The link of basic problem video is in the description below. Euler then went on to define a function known as Euler Zeta function. Euler's zeta function is defined for any real number x greater than 1 by the infinite sum. Zeta x is equal to 1 by 1 to the power of x plus 1 by 2 to the power of x plus 1 by 3 to the power of x, and so on. When x is greater than 1, the series converges. Euler himself calculated zeta 2, zeta 4, zeta 6, and many other zeta for even natural numbers. For odd natural numbers, zeta functions don't provide a closed form expression, but converge. While studying distribution of prime numbers, Riemann defined the Riemann zeta function as a function of a complex variable s that analytically continues the sum of the series. Zeta s is equal to 1 by 1 to the power of s plus 1 by 2 to the power of s plus 1 by 3 to the power of s, and so on, which converges when the real part of s is greater than 1. Now, for real part of s greater than 1, Riemann zeta function is an analytic function as it is expressed as a convergent power series. Now what about when the real part of s is less than 1, when the power series diverges? Thankfully, in complex analysis we have a technique called analytic continuation to extend the domain of a given analytic function. Through analytic continuation, we can define values of a function in the new region, where the power series initially defined becomes divergent. And what's more interesting is the fact that analytic continuation of an analytic function is unique. Riemann, in his paper, provides the analytic continuation of his zeta function when the real part of s is less than 1. If you wish to intuitively understand analytic continuation and are also interested in a $1 million prize, then I would recommend you to go to another wonderful YouTube channel, 3 Blue 1 Brown's video, visualizing the Riemann hypothesis and analytic continuation, whose link I will provide in the description below.
Riemann's analytic continuation expressed zeta function as this following functional equation: zeta 1 minus s is equal to 2 to the power 1 minus s pi to the power minus s sine pi by 2 into 1 minus s gamma s and zeta s. Now we'll put s as 2, then we can write zeta minus 1 as 2 to the power minus 1 pi to the power minus 2 sine pi by 2 into minus 1 gamma 2 and zeta 2. So zeta minus 1 is 1 by 2 1 upon pi square, and sine minus pi by 2 is minus 1. Now gamma 2 is factorial 1, which is 1, and zeta 2. Now we already know from Basel problem zeta 2 is pi square by 6. So pi square and pi square will cancel. So from here we'll get zeta minus 1 as minus 1 by 12, and zeta minus 1 is nothing but 1 upon 1 to the power minus 1 plus 1 upon 2 to the power minus 1, 1 upon 3 to the power minus 1, 1 upon 4 to the power minus 1 up to infinite, and this is minus 1 by 12. So from here we'll get this result: 1 plus 2 plus 3 plus 4 up to infinite, and this value is minus 1 by 12, and that is zeta minus 1.
Now, we will come to the most interesting part of the video. The weird mathematician's fantasy of finding the sensible value to the divergent sum has some applications too. One such use of the result is in the original version of string theory, which is Bosonic string theory. In somewhat informal terms, the theory assumes that if space-time has d dimensions, then each harmonic of the string can be viewed as a collection of d-2 independent quantum harmonic oscillators, one for each transverse direction. If the fundamental oscillation frequency is omega, then the energy in an oscillator contributing to the nth harmonic is nh omega by 2. If we sum over all harmonics across all dimensions, we get E is equal to minus h omega into d minus 2 into 1 plus 2 plus 3 plus 4 and so on whole by 2 is equal to minus h omega d minus 2 whole by 24, which implies that 24 should divide d minus 2. So, ultimately, it is this result and also Goddard-Thorne theorem which leads to the conclusion that for bosonic string theory to be consistent, it must have at least 26 dimensions, which is 24 plus 2. The regularization of 1 plus 2 plus 3 plus 4 and so on is also involved in computing the Casmir force for a scalar field in one dimension. Suppose you take two conducting metallic plates, place a few nanometers apart, and arrange them in a vacuum so that they are parallel to each other. According to classical physics, there shouldn't be any net force acting between the two plates. When this field is studied using quantum physics, it is seen that the plates generate a net force. This force is best described and more easily calculated in terms of the 0-point energy, which is the lowest possible energy that a quantum mechanical system may have. Loosely speaking, while calculating the wave energy in one dimension, we get the infinite sum 1 plus 2 plus 3 plus so on, which diverges, implying an infinite wave energy, which is obviously incorrect. But if we take 1 plus 2 plus 3 plus 4 and so on is equal to minus 1 by 12, then we get a finite result, which is consistent with the experimental results. So, in the end, Numberphile should be lauded for the effort which made mathematics accessible to millions of people and made people discuss Ramanujan summation and Riemann Zeta function. However, a little disclaimer at the end would have caused a lot less trouble.
Hello and welcome to the world of mathematics. I present my website www.mathsmarazine.com and my YouTube channel Mathsmarazine for your kind perusal. If you like them and are inspired by the possibilities, then consider subscribing and sharing it with someone you know who might benefit from it. Thank you.